Hi, I'm John Wolpert. I'm the Seeker of Awesomeness for Consensus Labs here in Washington, D.C. Consensus is a company that operates in many countries. We're the largest blockchain company right now in the world by many accounts, and one of the fastest growing software companies in the world, and by many accounts the largest blockchain company in the world. We help businesses start up on the new Internet of Transactions, on the blockchain, and in particular on Ethereum. So I'm here in DC with the team looking for new ventures to get behind, to help bootstrap and to get going faster. We're a new venture development lab. So my experience of the evolution of blockchain, which I think is pretty common, was a number of years ago hearing about Bitcoin and cryptocurrency and thinking that was novel and interesting. But I was at IBM at the time working on the Watson team. And that was artificial intelligence and pretty interesting unto itself, so I didn't pay it a lot of attention. Then a few years later, my boss, one of my favorite people at IBM, who's now the head of IBM Blockchain, Jerry Cuomo, called me up and he said, "Hey Louis, it's Clark." And I said, "Well, what do you want, Jerry?" And he said, "Well, there's this thing called blockchain. I mean, we don't know a lot about it, but there's gold in those hills. Go out and find it." And I said, "Well, give me a ship and crew and I'll go investigate." And he said, "Well, I got a canoe, 2 dogs, and a musket." And I said, "Well, okay." And then we got lucky. It turned out that blockchain was we got halfway across the Mississippi and looked over our shoulders and found that there was a wagon train behind us, and now we're running a boom town. And there was definitely there was a there. So we got lucky, and that's how I stumbled into blockchain. Every use case I've seen in industry to date since 2015 that tried to do something with blockchain, that said, "Hey, let's do this on blockchain," has every single one of them has proven why it doesn't need blockchain. And everyone that says, "Hey, let me look at this problem differently through the lens of immutability, of decentralization, of a number of nuanced ideas that are actually packed up into primarily public blockchain technology, especially around token economics and what you can do with this emergent notion of being able to not just gamify human interaction. Gamification is just keeping track of scores, but then turning that into an economic set of decisions, right? I'm going to vote, or I'm going to bet that this fact is true. Well, if the consensus is that it's false, I just lost not just a point, but real economic value in some way, either in money, real money, or some kind of other value, maybe voting points or something else. So it's applying this notion of powerful public blockchain is effectively a high precision instrument for seeing problems differently and then instrumenting them in ways that would have been way too expensive and difficult to do if we had the old rails only, right? We needed a new railway to run these kinds of transactions, one that's more nimble, one that's more precocious, more always available. And once you have that kind of new rails, you have an infrastructure that can allow you to just do things completely differently.
Welcome to the first course in the blockchain specialization titled Blockchain Basics. Let's start by asking ourselves, what is a blockchain? Why should you care about it? Unlike traditional methods, blockchain enables peer-to-peer transfer of digital assets without any intermediaries. It was a technology originally created to support the famous cryptocurrency Bitcoin. The blockchain by itself has taken a life of its own and permeated a broad range of applications across many industries, including finance, healthcare, government, manufacturing, and distribution. The blockchain is poised to innovate and transform a wide range of applications, including goods transfer, for example, supply chain, digital media transfer, for example, sale of art, remote services delivery, example, travel and tourism, platform for decentralized business logic, for example, moving computing to data sources, and distributed intelligence, example, education and credentialing. Additional applications of blockchain include distributed resources, for example, power generation and distribution, crowdfunding, for example, startup fundraising, crowd operation, for example, electronic voting, identity management, for example, one ID for all your life's functions, and government public records and open governing. Moreover, blockchain can enable an inclusive economy. It can enable a person in a remote corner of the world to partake in a democratic process. Opportunities for innovative applications are endless. There is a dire need for critical thinkers, designers, and developers who can envision and create newer application models on blockchain to benefit the world. This course is a first step in addressing this need. At the end of this course, you will be able to explain the three fundamental characteristics that define the blockchain using Bitcoin blockchain. Bitcoin is not the only player in town. By the end of the first module, we'll move beyond Bitcoin into introducing the next generation blockchains with Ethereum. You will also be able to discuss the important features of Ethereum blockchain that is used as a reference implementation in many newer blockchains, and explain the algorithms and techniques that enable the blockchain, including a public key cryptography and hashing. Finally, you will be able to outline methods for realizing trust in a blockchain. Let's begin with an introduction of Bitcoin. Two major contributions of cryptocurrency Bitcoin are a continuously working digital currency system and a model for autonomous decentralized application technology called the blockchain. Though our focus is on a general blockchain, we have to understand the working of the technology behind Bitcoin to fully appreciate the innovation of blockchain. We can all agree that the advent of the internet and the World Wide Web has transformed every aspect of our lives, from stock markets to street corner food trucks. It has enabled the technology explosion with Web 2.0 and the world of e-commerce applications. Around 2008-2009, when the institutions and markets we trusted were crumbling down and everybody was running away from the Wall Street, a mysterious person or persons called Satoshi Nakamoto introduced a new digital currency, a cryptocurrency called Bitcoin. Bitcoin enabled an innovative platform for peer-to-peer transfer of value without any central authority. With no central authority, how did Bitcoin realize trust and security? By implementing software programs for validation, verification, consensus in a novel infrastructure called the blockchain. Later on, in about 2012-2013, computational elements were added to the blockchain infrastructure that has opened up a whole world of possibilities beyond simple currency transfer. These innovations are significantly shaping the direction of Web 3.0, as you will learn in the next 4 courses. What is a blockchain? Blockchain is about enabling peer-to-peer transaction in a decentralized network, establishing trust among unknown peers, recording the transaction in an immutable distributed ledger. Let's understand centralized versus decentralized network using a common scenario. Consider a scenario where a customer wants to buy an item using her credit card. Let's enumerate the intermediaries involved in accomplishing this task. We have a credit card agency, we have a customer bank, we have a credit cards bank, we have an exchange, we have the merchant's bank, and finally the merchant. This is an example of a centralized system that we are so used to. Now compare this with a system where peers can transact directly with each other, irrespective of where they are located. Functions of the intermediaries are shifted to the periphery, to the peer participant in the blockchain infrastructure. Peers are not necessarily known to each other. This is a decentralized system. How do we establish trust among the peers in such a decentralized system? By having a process in place to validate, verify, and confirm transactions. record the transaction in a distributed ledger of blocks, create a tamper-proof record of blocks, chain of blocks, and implement a consensus protocol for agreement on the block to be added to the chain. So, validation, verification, consensus, and immutable recording lead to the trust and security of the blockchain. Now I'll explain these concepts using another scenario. I'm lending Amy $10,000. This is one single peer-to-peer transaction. We both make a note of it on a ledger. What if I change my entry from 10,000 to 11,000? Alternatively, Amy changes hers from 10,000 to 1,000. To prevent this trust violation, we need to seek the help of people around us, Lisa, Allison, and Francis. Provide all of them a valid copy of this ledger. This is the basic concept of an immutable distributed ledger defined in a blockchain process. In this scenario, we were all physically present in one location, Amherst. Now imagine this to be an online transaction to an unknown peer. Also, scale up the one transaction to 10,000 transactions. How about 1,000,000 transactions? I should be able to transact with equal ease to any unknown peer in Amherst, Albany, or Albania. Maybe to send some flowers to a friend in Albania. This is the tenet of a decentralized system supported by blockchain. In the case just described, how do we trust our unknown peers? Through verification and validation. In our example, Amy requests Kevin to verify the amount I transacted with her. Kevin checks it. Oops. Kevin finds the amount of transaction is not 10,000, but 300. Not valid. Kevin rejects and nullifies the transaction. Similar to this, validation and verification methods defined by the blockchain and implemented by the peers provide the collective trust needed in a decentralized system. Summarizing, blockchain technology supports methods for a decentralized peer-to-peer system, a collective trust model, and a distributed immutable ledger of records of transactions. Here is the basic structure of a blockchain. Transaction is the basic element of the Bitcoin blockchain. Transactions are validated and broadcast. Many transactions form a block. Many blocks form a chain through a digital data link. Blocks go through a consensus process to select the next block that will be added to the chain. Chosen block is verified and added to the current chain. Validation and consensus process are carried out by special peer nodes called miners. These are powerful computers executing software defined by the blockchain protocol. Let's now discuss the details of a single transaction. In Bitcoin, a fundamental concept of a Bitcoin network is an unspent transaction output, also known as UTXO. The set of all UTXOs in a Bitcoin network collectively define the state of the Bitcoin blockchain. UTXOs are referenced as inputs in a transaction. UTXOs are also outputs generated by a transaction. All of the UTXOs in a system are stored by the participant nodes in a database. Now let's review the role of the UTXOs in a Bitcoin blockchain. The transaction uses the amount specified by one or more UTXOs and transfers it to one or more newly created output UTXOs, according to the request initiated by the sender. The structure of a given UTXO is very simple. It includes a unique identifier of the transaction that created this UTXO, an index or the position of the UTXO in the transaction's output list, a value or the amount it is good for, and an optional script, the condition under which the output can be spent. The transaction itself includes a reference number of the current transaction, references to one or more input UTXOs, references to one or more output UTXOs newly generated by the current transaction, and the total input amount and output amount. Participants can validate the transaction contents. Does the UTXO's reference the input exist in the network state? This is the only one of the many validation criteria. Recall our demonstrated scenario. This is similar to Amy asking Kevin to verify the money in the envelope to be $10,000. Are these UTXOs valid? All right, it is time to explore a real transaction. It is available at this link. At the top left is the transaction number. Just below, there are 3 input UTXOs referenced, and an arrow points to the references of the 2 output UTXOs. Note that there are 3 input UTXOs and only 2 output UTXOs. This means that the total amount in 3 input UTXOs are spent to generate 2 new output UTXOs. Just below the output UTXOs is a total amount transferred in the Bitcoin value. That is shown in green. Let's now move on to learn about a block. As you can see, a block is composed of a header of information about the block and a set of valid transactions. At first, we'll examine the Genesis block. It's available at this link. We introduce this block number 0 for posterity's sake. This is where it all began. Satoshi Nakamoto initiated the Bitcoin blockchain with one transaction of 50 Bitcoins or 50 BTC. This one transaction created a UTXO output for Hal Finney's address. The date of the blockchain creation is January 3rd, 2009. There was no previous block. This field is all zeros. It also lists a block reward or miners fees of 50 BTC. We'll discuss miners reward in a later lesson. Let's now look at the more recent block 482808. On the right panel, note the current block hash. The previous block hash, that is a link to the previous block, and on the left panel, down here, the nonce. You will learn about the block hash computation in the module quiz and in the later lessons. Now let's look at the structure of the blockchain by peeking into the Bitcoin blockchain. Our goal is to understand the link between the blocks. Let's consider the chain of 3 blocks: 488867, 488868, 488869. 488868, shown in the middle, has the hash of 488867 as its previous hash. Block 488869 has the hash of 488868 as its previous hash, forming the links in the chain. To summarize, transactions bring about transfer of value in the Bitcoin blockchain. The concept of UTXO defines the inputs and outputs of such a transaction. Once a block is verified and algorithmically agreed upon by the miners, it is added to the chain of blocks, namely the blockchain. Now that we have reviewed the basics of a blockchain and its basic structure and origin, let's consider the basic operations in a blockchain. Operations in the decentralized network are the responsibility of the peer participants and their respective computational nodes, for example, laptop, desktop, and server racks. These operations include validation of transactions, gathering the transactions for a block, broadcasting the valid transaction in the block, and consensus on the next block creation, and chaining the blocks to form an immutable record. In this lesson, we explore some of the fundamental operations of the Bitcoin blockchain. First, we have to discuss the participants. There are 2 major roles for the participants. Participants that initiate transfer of value by creating a transaction, additional participants called miners who take on added work or computation to verify transactions, broadcast transaction, compete to claim the right to create a block, work on reaching consensus by validating the block, broadcasting the newly created block, and confirming transactions. You might wonder why a participant would take on additional work. Well, The miners are incentivized with bitcoins for their efforts in managing the blockchain, as we'll find out. Transaction validation is carried out independently by all miners. The process involves validation of more than 20 criteria, including size, syntax, etc. Some of these criteria are: referenced input unspent transaction output UTXOs are valid. Recall, UTXOs were defined earlier in lesson 2. Reference output UTXOs are correct. Reference input amount and output amount match sufficiently. Invalid transactions are rejected and will not be broadcast. All the valid transactions are added to a pool of transactions. Miners select a set of transactions from this pool to create a block. This creates a challenge. If every miner adds the block to the chain, there will be many branches to the chain, resulting in inconsistent states. Recall that blockchain is a single, consistent, linked chain of blocks. We need a system to overcome this challenge. The solution? Miners compete to solving a puzzle to determine who will earn the right to create the next block. In the case of Bitcoin blockchain, this puzzle is a computational puzzle and is central processing unit or CPU intensive. Once a miner solves the puzzle, the announcement is broadcast to the network and the block is also broadcast to the network. Then other participants verify the new block. Participants reach a consensus to add a new block to the chain. This new block is added to their local copy of the blockchain. Thus, a new set of transactions are recorded and confirmed. The algorithm for consensus is called proof of work protocol, since it involves work or computational power to solve the puzzle and to claim the right to form the next block. Transaction 0, index 0 of the confirmed block, is created by the miner of the block. It has a special UTXO and does not have any input UTXO. It is called the coin-based transaction that generates the miner's fees for the block creation. Currently, the miner's fees is 12.5 BTC for Bitcoin. This is how new coin is minted in Bitcoin. To summarize, the main operations in a blockchain are transaction validation and block creation with the consensus of the participants. Yet, there are many underlying implicit operations as well in the Bitcoin blockchain. Let's now look beyond Bitcoin. Bitcoin blockchain is open source and the entire code is available on the GitHub. During the initial years beginning roughly in 2009, this open source code was extended to release different cryptocurrencies. About 300 plus cryptocurrencies were introduced. Bitcoin supports an optional and special feature called scripts for conditional transfer of values. Ethereum blockchain extended this scripting feature into a full-blown code execution framework called smart contract. A smart contract provides the very powerful capability of code execution for embedding business logic on the blockchain. Based on such capabilities, three major types of blockchains emerge from Bitcoin Foundation. Type 1 deals with the coins and cryptocurrency currency chain, example Bitcoin. Type 2 supports cryptocurrency and a business logic layer supported by code execution, example Ethereum. Type 3 involves no currency but supports software execution for business logic, example the Linux Foundation's Hyperledger. With the addition of code execution comes the serious consideration about public access to the blockchain. Hence the classification of public, private, and permission blockchain based on access limits. We have been watching Bitcoin blockchain continuously operational since its inception, all supported by its public participants. Thus, Bitcoin is a fantastic example of a public blockchain class. Anybody can join and leave as they wish. Transaction blocks in the blockchain are publicly observable, even though participants are anonymous. It is open source. You can also create new coin digital currency by modifying the Bitcoin code. Wallet applications provide the basic interface to transfer value through the Bitcoin blockchain. In a private blockchain, access to the blockchain is limited to selected participants. For example, those participants within an organization. This restriction helps in simplifying the normal operations such as block creation and consensus model. The third classification of blockchain is permission blockchain, also called consortium blockchain. It is meant for a consortium of collaborating parties to transact on a blockchain for ease of governance, provenance, and accountability. For example, a consortium of all automobile companies or healthcare organizations. Permission blockchain has the benefits of a public blockchain, with allowing only users with permission to collaborate and transact. In summary, significant innovations such as smart contracts have opened up broader applications for blockchain technology. Private and permission blockchain allow for controlled access to the blockchain, enabling many diverse business models.